Okay, hello, good evening. Hi, Karen. Haven't seen you in a while. How are you doing? Uh, so whose class did you attend previously? The previous few weeks? Did you any? Chilling, nice. Whose class did you attend previously? And I don't know whether the progression is the same because it might be a bit different because I'm going into velocity time graph today. Velocity time graph. Have you learned this? Maybe you have, but I'm until here. Okay, last week I actually thought, oh, what about previous few weeks? Whose class did you attend? As in here in DDC? Whose class did you attend? Did you attend Yiqing or Hanyi's class? Because their speed might be different. Not to say might, but it must be different. Okay, because very seldomly we have the same speed. Okay, so let me repeat. We have displacement time graph last week. Okay, and the gradient for displacement time graph is the velocity. Okay, it's the velocity. That means for this graph, how is the car moving? How does the car move? The car goes forward with a steady speed. The car stays not moving. Okay, because you see, positive gradient, positive velocity. Positive velocity means the car goes forward. Zero gradient, zero velocity means the car stays. Positive gradient again, positive velocity again, the car goes forward again. Negative gradient, negative velocity, so the car goes backward. Everything is done with a steady speed. Steady speed going forward, stay, steady speed forward, steady speed backward to the original point. Am I making sense here? Am I making sense here? So velocity time graph, this is where things starts to get a little bit more confusing. Why? Because according to velocity time graph, gradient is the acceleration. Okay, gradient is the acceleration. Okay, so let me put it this way. You see, we have displacement divided by time equals to velocity. Velocity divided by time equals to acceleration. Okay, so last week we were looking at displacement time graph, isn't it? Oh, okay. As in sasaran at halaju. Okay, so okay, if you see displacement, sasaran, the graph just now, this is your graph sasaran muscle. Okay, so the sasaran gradient is going down, divide by time. Okay, so this is gradient. This is gradient. Okay, so displacement time graph, the gradient is velocity. Just now. Now, velocity graph, halaju, the gradient is acceleration, pecutan. So whenever we talk about gradient, we go down according to here. Displacement graph, gradient, velocity. Velocity graph, gradient, acceleration. Okay, and of course, there's the area lah. There's the area under the graph lah. Luas permukaan bawah graph. Okay, but okay, anyway, let's look at how is this graph. What does this graph means? Okay, so can you see the beginning? Positive gradient. Positive gradient, positive acceleration. What is positive acceleration? What is pecutan positive? That means the car goes forward faster. Okay. Let me draw you another displacement time graph. Let's say this is displacement, pecutan, and the graph looks the same. Okay, let's say the graph looks the same. Okay, just now, the car goes steady speed forward. Now, the car goes, it goes faster. Can you see the difference? Can you see the difference? That's why displacement graph, sasaran graph, and your hal laju graph, velocity graph is very different. Okay, and then just now we learned zero gradient, zero velocity. Okay, kecerunan kosong, hal laju kosong. Okay, hal laju kosong, zero velocity means the car is staying in place, not moving. But now, zero gradient, zero acceleration. Kecerunan kosong, kecerunan sifar, pecutan sifar, pecutan kosong. Okay, if my pecutan is kosong, if my acceleration is zero, that means I am still moving forward. Because this part is steady velocity. Okay, steady hal laju. You get what I mean? If I drive here to Penang all the way 80 kilometers per hour, am I moving? I'm moving, isn't it? But am I accelerating? Am I going faster? If I drive all, I mean, it's not possible to drive all the way 80 lah. But let's say I drive all the way 80. Let's just say, am I accelerating? Am I becoming any faster or any slower or any change in my speed? You get what I'm trying to say? You get what I'm trying to say? Okay, I'm not changing my speed, isn't it? My acceleration, my pecutan is zero, but I am still moving forward. Just now, the car, displacement graph, your sasaran graph, stay, not moving. Your hal laju graph, velocity graph, the thing goes forward, steady speed. Okay, the car goes forward, steady speed. So this is what you need to see the difference. Okay, the last part, negative gradient, negative acceleration. Okay, kecerunan sifar, kecerunan negative, pecutan negative. What does it mean by pecutan negative? Means the car slows down. I step on the brake, my car slows up. The car goes, just now is, this part is, now is, okay, slows down. All right. My car slows down, I still go forward. Am I making sense? When your dad or your mom steps on the brake, the car is still moving forward, right? Whereas this part, negative gradient, negative velocity. Okay, hal laju negative, the car reverse backward. This is the car reverse. So you see the difference? For your sasaran graph, the car goes steady speed forward, not moving, then steady speed backward. This is steady speed moving, right? Becoming faster, stay, becoming slower. They still move forward, still moving forward. See the difference? See the difference? This is where things gets a little bit confusing. I don't know lah. I like to always write it down. When I see displacement, sasaran, I always like to write gradient. Okay, kecerunan is the velocity, hal laju. Okay, when I see velocity, hal laju, kecerunan, pecutan. I write it down, then I won't get confused. Okay, and you just follow everything according to what you write now. Make it a habit. All right. All right. But of course, there's one more thing here. There's one more thing here. Can you see the area here? The luas bawah graph. This graph here, this bottom part here, it means the displacement. Okay, because for this graph, this the area is to go up. The loss is to go up. Why this one's the sasaran graph, no area? Because go up, there's nothing. But this one, velocity, go up, there's something. Okay, so area is the displacement. The loss is the sasaran. Am I making sense here? Am I making sense here? The worst case scenario is you memorize this, you go in exam, you write down, then you follow. Am I making sense here? I hope I am. I hope I am. This one you need a lot of practice one. I mean, it will get a bit confusing when you first do it. It takes better. Kecerunan to pecutan. Yes, okay, kecerunan pecutan is the graph today. Last week is kecerunan halaju. You just go one step forward, you see? Sasaran, halaju, pecutan. So when your graph is sasaran, you go one step forward for the kecerunan. Kecerunan is one step forward, so that's the halaju. So if your graph is halaju, one step forward, kecerunan is the pecutan. Okay. Yeah. That's the best way is to draw this, because I don't want you to die memorize like this, because you'll forget one. Okay. So right, let's look at number one. Okay, you see we see the motion of a ball, blah blah blah. How velocity, how laju. So you write down gradient is the acceleration. Okay, or if you say kecerunan is the pecutan, okay, in BM. And of course, you have area here. Luas is the displacement. Sasaran. Okay, whenever you see this, you write the formula down, then your life will be easier. Okay, so A. Hey, where's my... Sorry, my pen has no more battery. Okay, give me a moment here. Okay, so let's look at A. What is the displacement, sasaran, of the ball in the first 4 seconds? How do you find the sasaran? How do you find the displacement? How do you find the sasaran? How do you find the displacement? The displacement, the sasaran, is the luas. Correct? Correct? The luas permukaan. So they want where? They want first 4 seconds. 4 saat pertama. So first 4 seconds is here. So the area is here. They want the luas here. So what's the luas here? 4 long, yeah. 4 meter. Easy, right? Okay, next. Acceleration. Pecutan. How do you find pecutan? Yes, simple math. How do you find pecutan? How do you find pecutan? How do you find acceleration? According to our formula, how do you find acceleration? How do you find pecutan? You find the kecerunan, the gradient. Do you remember how to find kecerunan? They want 8 to 12 seconds. From 8 here to here. What's the formula for kecerunan? This is lower form math. This is mathematics of lower form. Okay, so we write down the coordinate first. This is 8, 3. This is 12, 0. This is okay? So this is x1, y1, x2, y2. Yes, so you just put everything in now. So 0 minus 3 over 12 minus 8. So it's negative 3 over 4. So if you put it into decimal, negative 0.75 ms minus 2. Can follow formula. If you forget this or die, you cannot do anything on. Hey, I have a question here. I have a question here. If the area looks like this, how do you calculate this area? How do you calculate this area? How do you calculate this shape? Do you remember? Okay, that's the stupid way. That's the smart way. Yes, splitting it is the stupid way because you have to calculate the triangle first, then the rectangle, and then the triangle. The smart way, if you remember, this thing is called a trapezium. No, you cannot times two in the middle. You cannot. If you remember, this is called a trapezium. So for the formula for trapezium, if this is a trapezium, but you see the first question is not a trapezium. But if this is a trapezium, the formula is 1 over 2 times a plus b times height. Remember, height is this. A plus b is a plus b. The upper line and the lower line, you add together. Height is the height. Okay, can? This is the easy way lah. The easy way lah, the smart way lah, because you don't need to do so many steps lah. Okay, so come, can you try number 2 and number 3? I'll wait for you to do, and I'll give you the answer. Okay, don't worry, just try. Wrong, never mind. It's okay. Follow this, follow this, because this is your halaju graph, this is velocity graph. You may start now. Okay, are you done with question 2? Are you done with question 2? Just question 2? Are you? Yes? Okay, good. Okay, so A, you see, velocity is the halaju. This one no need to calculate one. Because the graph itself is already halaju. No need to calculate. So 4 second, 4 second, 10. Yeah, because I usually there's two more. I don't know where they are today. But lately has been heavy rain lah, so most of them get home late lah. So I don't blame them. Must be a reason like this. Okay, so 8 second, 8 second, 15. No calculation here. Okay, next, displacement, sasaran. Okay, sasaran is the area, the luas. You see this one, from 0 to 10. From 0 to 10, that means here, that means here. This is a trapezium, right? This is a trapezium. Anything with two parallel sides and it has four sides, then it's a trapezium. Okay, so 1 over 2, the height is 15. A is 4. Sorry, A is 4. Then B is 10. So the answer is 105. Is this your answer? Hope this is your answer. Okay, and I'll wait for you to finish question 3. And we're going to question 3. All right, are you done? Are you done? It's a long question, I know. Last question. Okay, cool. Okay, I'll give the answer. You check while you do. Okay, velocity. How large you? This is here. So it's 10. Time taken to reach 5 is here, 2 seconds. Acceleration, pecutan, this is the gradient. from 0 to 6. That means here. So this is 6, 15. This is 0, 0. 15 minus 0 over 6 minus 0. I mean, minus 0 need to write. It's a working, right? To show that this is your working. So answer is 2 point. Is your answer good so far? Are your answers good so far? Are your answers good so far? So total displacement, that's the sasaran. So that's the area. So 1 over 2 times height times A here, 6 plus 12. So the answer is 135. Is this the answer? Is this the answer? Okay, so what about hal laju? Average velocity, hal laju purata. That's when you use the total displacement, jumlah sasaran, divide by time. So what's your jumlah sasaran? Then you got it here, what? So 135 divided by 12, 11.25. Is this the answer? Is this the answer? Okay, good. Good. So I'm gonna jump over this graph. No more. Okay, so you go and do the exercise yourself because we actually have plenty. Go and do it yourself and go and check the answer. You see, a lot of it actually. I'm not going to discuss. You go and do it yourself because it's very repetitive and it's the same thing over and over again. Okay, so guys, we are going, guys, we are going to talk about gravitational acceleration today. Okay, so what is this? This is the last part of today. I don't think I can go to inertia today. Okay, so what is gravitational acceleration? This is called Bertrand gravity. Yes, just me and you. Okay, Bertrand gravity. Okay, what does it mean? What does it mean? What is gravitational acceleration? Okay, you see, when you jump down from a building, you accelerate down, isn't it? You're becoming faster. You don't just you go like that. You accelerate down, isn't it? Okay, you accelerate down. You accelerate down because of the gravitational force. Because of the dire gravity. The dire gravity pulls you down. So as it pulls you down, you will get the gravitational acceleration, Bertrand gravity. Okay? And here's the thing. No matter where you jump, no matter how high you jump, no matter when you jump, I don't care. Your gravitational acceleration, the Bertrand gravity, will always be 9.8. Okay, in lower form, we used to say 10, but now we say 9.8. And we represent this using G. G is the Bertrand gravity. Gravitational acceleration is 9.8. That means if you jump from Malaysia's building, you jump from France building, you jump from the plane, you jump from space, you will accelerate at 9.8. Okay, you will accelerate at 9.8. Okay, so I have a question here. I have a question here. Okay, it doesn't how heavy you are. It doesn't matter how heavy you are, you will get 9.8. Do you understand what I mean? Do you understand what I mean? Let's say you are 50 kg, I'm 80 kg. We jump down at the same time, we will get the same G. We will get 9.8. So according to this logic, right, I do have a question here. According to this logic, if I throw a piece of feather and I throw a bowling ball at the same time, they both have 9.8, isn't it? Make sense? So according to this logic, they will reach the ground the same time. This is what Newton said. But if you use your common sense, does it make any sense? No, isn't it? So does it mean Newton is wrong? You see, so far what we explain here, it makes sense, isn't it? But they don't reach the ground at the same time. When you do this in real life, it doesn't obey. It doesn't, you don't get that. So what gives? What's wrong here? What's wrong here? Because there is something that we forgot to consider. Okay, let me ask you, when you jump down from a building, what do you feel? Air. Good. So this is what we have ignored. This is called air resistance. Bintangan udara. When you jump down, there's some air pushing you, isn't it? Okay, so in this case, air resistance, okay, let's say the air resistance is 100 Newton, shall we? Let's say, for example, 100 Newton for a 2000 Newton heavy ball. The bowling ball is around 2000 Newton. Sorry, 2000 Newton, 20, whatever lah. Okay, this air resistance for the bowling ball is no big deal, isn't it? Because the air resistance is so small. So the bowling ball just continues to go down very quickly. But this 100 Newton for this feather is something. Is something quite big, isn't it? So that's why the feather just kind of goes around because of the air resistance. So it will reach the ground really slowly. Okay, so how do we prove Newton is right? How do we prove that Newton says that both will reach the ground at the same time? How do we do that? How do we do that? Put them in a sack. No need lah. Why put them in a sack? Like, okay, the easiest way to prove Newton is right is to take the air away. Correct? If there is no air resistance, they have the same G, they should reach the ground the same time. Am I making sense? Am I making sense? Yes, you use a vacuum chamber. That's correct. Very smart. Okay, so someone actually did this. Okay, someone actually did this. And this makes a lot of sense. Okay. Okay, this is non-vacuum first. You see, this is non-vacuum. This is what our logic tells us. The ball will reach first, isn't it? Okay, because of the air resistance. Okay, but when you take the air away, you see this guy actually went the distance and did it in a vacuum. Make sense? Make sense? So Newton is never wrong. Newton is never wrong. Okay, it's just that we don't see it in real life because there's no vacuum. It's impossible to have vacuum and you drop things down. Okay, that means about the, of course lah, cause it's heavier, ma. Okay, so what's this situation that, okay, there is a name for it. There is a name for it. If there is no air resistance and they drop at the same time, we call this free fall. Jatuh bebas. Okay, free fall is when there's only gravitational force. There's only direct gravity. No air resistance, no nothing. Okay, no, there's only gravitational force. No air resistance, no friction, no nothing. Okay. Hi, Elena. You figure out how to join the class? I'll send you the recordings later. I'll send the recordings later. Okay. Right. So free fall is when there is a What am I saying? Okay, free fall only happens in vacuum. Okay, free fall only happens in vacuum. If there is no vacuum, if there's air, it will never be free fall. Okay, so you can practically say free fall is literally impossible in the world. In this world, unless you do it like just now, like you draw the vacuum out, it's almost impossible. All right, so you see, this is free fall. The feather and the stone, like I said just now, the feather and the bowling ball, they will drop down at the same time, which is mind-blowing because it makes no sense. But this is what we do in real life. If you throw a feather, and if you throw a stone, the stone will reach the ground first, and then the feather will just kind of float around because of the air resistance. Because of the air, rintangan udara. Thanks for the reminder. Okay, so you guys okay? You guys okay? Lina, this might sound like alien stuff to you, so but I will send you the recording later. Okay, make sure you watch. Make sure you watch. Okay. Anyway, so this is free fall, guys. This is free fall. Oh, there's no calculation here. There is no calculation here. So praise the Lord. The last calculation was done just now. Okay. So this is only gravitational force and free fall. Yes, just logic, exactly. Okay, so again, if they ask you what is free fall, what is jatuh bebas, that means there's only gravitational force. Hanya mempunyai daya gravity saja. No air resistance, tiada rintangan udara, no friction, tiada geseran. Okay, so if you were to jump a parachute in a free fall, your parachute wouldn't work. You would just crash to the ground with huge speed. Okay, with crazy speed. You just don't slow down because there's no air to slow you down. Okay, guys, shall we go to the next part, which is inertia? Okay, this is the last part of the chapter. And can you please put a star here? Can you please put a star here? Guys, this inertia is super important. Okay, because it's coming up for exam. Okay, because it is coming up for exam, for sure. Okay, for sure. All right, so guys, any of you heard of what is inertia? Any of you heard of what is inertia? Anyone? Anyone? What is inertia? This is actually Newton's first law. Okay, Newton has 3 laws of motion. Karen, have you learned this already in school? Have you? Or haven't? When cars slow down, doesn't fully explain. Okay, guys, according to Newton, what is inertia? Inertia is the natural tendency of an object to resist any change in its original state. Still don't get it, isn't it? Still makes no sense, isn't it? Okay, guys, I like to put it in a very easy way. I like to put this in a very easy term. Okay, how do I explain inertia to kids? You see, because if I can make a kid understand, I will make you understand. Okay, yes, something like that. Oh, Alina, you know what is this? Okay, so to put it simply, things at rest stay at rest. Moving things stay moving. Okay, that means if you are at rest, if you're not moving, you would try your best not to move. If you are moving, you will try your best to keep moving without stopping. This is inertia. Okay, to put it simply, if you have a heavy rock, let's say a 20 kg rock, all right? If the rock is not moving, if it's at rest, you try to push it, the rock will say, no, I don't want to move. So the rock stays. Okay? The tendency of the rock to stay there, to not move, it's called inertia. Because the thing is at rest, it will try to stay at rest. It will try to resist you. You try to push it, the rock will say, no, I won't let you push. The resistance. Okay? And the other way around, if now let's say this rock is rolling down a hill, a 20 kg rock rolling down a hill, can you stop it? Should you stop it? Should you stay in front and block it? I mean, you can try, but you'll most likely be run over. Okay, so you see, this is another case. That rock is rolling down, it is moving. It will try its best to stay moving. You want me to stop? I don't want to stop. Just now was, you want me to move? I don't want to move. Now it's, you want me to stop? I don't want to stop. You see, this tendency to keep moving, this want to keep moving, it's called inertia. Okay, now the same story goes when you take a bus. Okay, when you take a bus, when the bus is not moving, you are not moving. All right, the bus is at a bus stop, let's say. The bus not moving, you not moving. When the bus starts to move forward, you have inertia. You would want to stay because staying at rest will want to stay at rest. You would want to stay. So when the bus moves forward, you will go backward because you say, no, I don't want to move. I want to stay where I was. So inertia. Okay, things at rest, stay at rest. The bus wants to move, you don't want to move. So you go backwards. All right. And then the other way around, when the bus is moving now, you are moving also. But when the bus slams on the brake, your body says, no, I don't want to stop. Just now, I don't want to move. Now, I don't want to stop. So the bus stops. You don't want to stop. You will crash forward. Okay? Moving things will want to stay moving. The bus says, we need to stop. Your body says, no, I don't want to stop. I want to keep moving. So you go. Make sense? Make sense? So that's the meaning of inertia. Right. Guys, you might have heard of inertia, but have you heard of sleep inertia? This thing is a real bitch. Okay? You see, everyone has sleep inertia. Whether yours is strong or not, it depends on you. My sleep inertia is goddamn bloody strong. How do I say so? I'm sure you experience this stupid dilemma every night. You want to sleep, but your body doesn't want to sleep. You just roll on a bed. Guys, how fast can you fall asleep? Are you the type that just falls asleep in seconds? Or are you the one just kind of lie there and think about life for like half an hour or 1 hour before you can fall asleep? Which one are you? Are you the first or the second? Because I'm definitely the second. Yes. You see, you want to sleep, but your scumbag of a brain just say, hey, let's not sleep. Let's think about. You remember that time you did some awkward stuff, and you're like, oh my God. It's when it's at night, your brain starts to dip into all this stupid memory and think of a time that you did something really awkward. You just feel like dying. Okay? And then in the morning, things just goes the other way. Now you're asleep, your body refuses to wake up. Okay, guys, tell me something. If you are the second type just now, you are the type that's very hard to fall asleep. Trust me, in the morning, you are the type that is very hard to wake up. Because I'm exactly this way. It takes me an hour to wake up. It takes me an hour to fall asleep. This is just how I work, right? So in the morning, I'll just kind of wake up, snooze my alarm for like 6,000 times, then kind of roll around, scroll Facebook or IG a little bit just to get my brain awake. Yeah, I see, you get what I mean, right? So guys, there is a term for it. It's called sleep inertia. When you are at rest, you want to stay at rest. When you're moving, you want to stay moving. When you're asleep, you want to stay asleep. When you're awake, you want to stay awake. This is what we call sleep inertia. Is there any way to improve this? No. Sleep inertia is usually born, right? I have friends who can fall asleep in 5 seconds, right? Like at night, right? Okay, he just lie down. Okay, we went camping. He just lie down you count to 5, he's snoring. You see, I envy people like this, right? And in the morning, he can just wake up, no problem. Like, book, snap, he's awake. Okay, while you are dragging your ass to get out, like, right? So that's your sleep inertia. Okay, am I making sense here, guys? The heavier you are, the higher the mass, the stronger the inertia. A bus is harder to move than a car. A bus is harder to stop than a car. Correct? Correct? Unless it's only urgent lah, then you want to wake up lah. Okay, guys, am I making sense here? I think I'm gonna end it here lah, because next week I'll finish this inertia thing, and we'll go to exercise. Okay, so next week we will stay one more week here before we jump to the next chapter. Okay, we are in no rush because this is the second last chapter already. We have one more chapter remaining, chapter 12. So no rush. Okay, no rush. So guys, are you okay? Alina, can you WhatsApp me personally? I will send you the recording later. Please go and watch it. Okay, so guys, have a good Wednesday. Okay, I will see you next week. All right, have a good one. See you. Bye bye.